Hello. For this exercise, you'll be needing some materials to actually go along, like the pencil that would assist you in doing all your drawings, the eraser for cleaning in case of any error, the ruler to make straight lines, and transparent paper on which most of our works will be done. You'll also need the log graph sheet. This would help us in plotting the field data. You need a master curve, very important. You need the auxiliary curves, also very important. And you need a calculator to make basic calculations. Once you have all this, you are set to go along with this tutorial course. And you also need the table, of course, and your heart and mind to be able to follow along. Transparent sheet for this exercise. Place your log graph sheet on the table, and before you continue, I'd like to tell you that the vertical axis for your log sheet stands for the apparent resistivity, while the horizontal axis serves as the current electrode spacing, which is AB/2. The field data we'll be working with is as shown on the right hand side of the screen. And bring your transparent sheet, place it gently on the log graph sheet and roll out the border as shown. Be careful about rolling your border, and then take off your log sheet in order to view the transparent sheet properly. It just should look like this. Then you label as follows: 1, 10 and 100. Also on the x-axis 10, 100, 1000. Or you can label anyhow you want to, but make sure you abide by the rules. You can see they are all in circle. So depending on your choice of scale, you can organize yours the way you want to. So having said all this, see you in the next lesson. Choice of scale for my graph here because of the data I'm working with. And you can also do yours if you're interested in doing that. And there's something I want to bring to your notice. Plotting on the log graph sheet is a bit different from plotting on the normal graph we're used to in our secondary school days, that is the linear graph. For this, if you look closely, you have circles of tens. From 10 you have 100, then you have 1000, and in between all these there are minor axes. The major axes are in tens and the minor axes, and these minor axes are being calibrated in a form such that it could be in 2 units, and at times it could be in a single unit, and at times it could be in 5 units. When it's in 5 units, you'd have just a minor axis between 2 major axes, and when you have about 10 minor axes, you should know it's in single one. But the more you practice, the more you know it anyway. Just try and plot yours. Yours should look like this at the end of the day. See you in the next lesson. I would want us to draw a smooth curve through our data point. Very good. And I think at this point we need to bring in our master curve in order to start the journey of getting out our K1. Where is my master curve? Now you place it gently such that the line of your border is parallel to the vertical line on the master curve, and also check out the curve that fits into part of your curve. I've seen mine and it fits it up to here. I've marked it. Now I'll check the value of the curve, and the value seems to be 2. I'll make a cross on the origin and then go to my auxiliary curve to trace out that value of 2, which is corresponding to this very curve. It's very important. So here is my auxiliary curve, and all I need to do here is just to trace out the value of 2 starting from the origin. just like this. Yes, just trace it out gently. Aha, very good. So when I take off my auxiliary curve, my transparent paper should look like this. You have your K1 equals 2. Make sure you write it there in order not to forget the value of the K. This is how your transparent sheet should look like. So now we'll continue matching the other part of our curve. That's why it's called partial curve matching. I'll place it on my master curve again. Check out the part of the theoretical curve that matches with my field points. I've gotten this. I'll mark it and then check out the value of that curve, and this is 1.5. I'll cross the origin and then put my K2 equals 1.5. Then I'll take my transparent sheet back to the auxiliary curve and then place the K2 cross on the origin and look out for the curve for 1.5 and then trace it out from the origin like we did for the first K. You need to be very careful in tracing out your curves too, and also make sure that the curve is passing through the origin. Very, very important. Yes, like that. So your transparent sheet should look like this. See you in the next lesson. Seem more like an ultimate search, right? Yes, K3, here we come. We're getting out our master curve again, just like the traditional way, and then trying to match the remaining parts of our curve. Somewhere here with the beta, so I'm going to put my cross at the origin, and the curve seemed to me to be 7. Yeah, K3 equals 7. And then in order to fulfill our righteousness, I would take this sheet back to the auxiliary curve to trace out the curve of 7. So the previous traced out curve should pass through the origin. Your cross should be at the origin and the line should be parallel to, and trace this out. Okay, yeah, then you can take this off to see what your sheet looks like. That's a transparent sheet. This is what it should look like. We are free from finding our keys. See you in the next lesson. This morning when I woke up, I had my devotion, brushed my teeth, took my bath, and I ate my breakfast. Why am I saying this? I don't know. Maybe because I just want to. So let's go to the business. We're looking for DNDR. To get your DNDR, you place your first cross on the origin and you read off the value closer to the second cross. In this case, the value down to this curve closer to my K2 is 2. Yeah, you can see the curve in that box. So my DNDR1 would now be 1.9 because the cross is not actually on that curve of 2, but very, very close to it. So 1.9 is close to 2. That's why I would make it 1.9. You can just highball it. Yours could be lower than that. And to get the second one, you put the K2 on the origin and read off the value of the curve that is close to K3. And in this case, if you look closely, the value falls on 7. Yes, this is 7 here. So the value of the box for the K3 of the 7. So therefore my DNDR2 will be 7. So it's time to calculate the layer resistivity and thickness. But if you look closely, you would see that one of our cross, that is the first cross for K1, is outside the graph sheet. and to accommodate for this, I would readjust the position of my transparent sheet just like this. Okay, and then when I read off the value of the K1 down towards the x-axis, I would have the thickness of the first layer, and when I read it off to the left hand side towards the y-axis, I would have the resistivity value for the first layer. But when it comes to K2 and K3, I wouldn't be having the layer resistivity and thicknesses, but ρ2 replacement and H2 replacement. The same thing goes for K3. So I wouldn't look for this for you, since you have the basic knowledge of what you are meant to do. So get out the ρ2 replacement and H. Now it's time for calculations. Don't be scared, they are just little ones though. And this is the formula that we'll be using for the calculation. ρ2 equals ρ1 times K1, ρ3 equals ρ2 replacement times K2, ρ4 equals ρ3 replacement times K3. If you have ρ5 in your case, ρ5 will be equal to ρ4 replacement and K4, and so on and so forth. And the same thing applies to the H1, H2, H3, H4 too. So from our results so far, we have our ρ1 to be equal to 32 ohms while K1 is 2. ρ2 replacement is 42 ohms while K2 is 1.5. ρ3 replacement is 58 ohms while K3 is 7. H1 equals 0.95. H2 replacement is 2.9. The NDR1 is 1.9 and the NDR2 is 7. So I like arranging mine this way because it makes my calculation very easy. So let's go on to the calculation. ρ2 equals ρ1 times K1, which gives us 64. ρ3 equals ρ2 replacement times K2, which gives us 63. ρ4 equals ρ3 replacement times K3, which gives us 406. For H2, that is the thickness of the second layer, that equals H1 times the NDR1, which gives 1.81. The thickness of the third layer equals H2 replacement times the NDR2. So the result from the product of these parameters gives the layer resistivity of layer 1 as 32 ohms, the resistivity of layer 2 as 64 ohms, the resistivity of layer 3 as 63 ohms, the resistivity of layer 4 has 406 ohms, while the thickness of layer 1 is 0.95 meter, thickness of layer 2 is 1.81 meters, and 3 is 20.3 meters. So we'll see in the next lesson.